Dear students, welcome to our last topic of Module 3, in which we are going to talk about the most awaited concept of singular value decomposition. As part of videos on SVD, I will discuss about the basic concept and we will put all the concepts we have learned up to now into SVD. Then in next video, I will talk about K-rank approximation, that how we can apply the concepts that we learn as part of SVD to reduce the dimensions of a dataset. While doing all these things, we will try to do all the stuff as intuitively as possible so that you can use them for from applied perspectives also. Now, SVD is referred as the central matrix decomposition method in linear algebra, and it is also referred as the fundamental theorem of algebra. So this is a big name given that there are so many fundamental things that we learn as part of linear algebra, but this is what the Strang et al. Gilbert Strang is a renowned mathematician, and you might watch some of the very interesting videos on YouTube from his course. But the point here is that SVD is highly revered, and there is a right reason that we will learn thanks to its universality and applicability to any kind of matrix. Now, in our last videos, we specifically looked into certain aspects of eigen decomposition, where we were saying that if we have a square matrix, specifically when it's symmetrical, we can always write it in the form of, or we can always diagonalize it, and we can write it as PD, P transpose, and we would say that A and D are similar matrices. Now, question arises, what would happen if our matrix is neither square, and if it is not square, then there is no question about it being symmetrical or not symmetrical. So the fundamental theorem of SVD theorem states that if AM cross N is any rectangular matrix, and it can have any rank R, which would be the minimum of it, which can be between 0 and minimum of M and N. And in that case, we can factorize our rectangular matrix M cross N into three components, what we say as U, sigma, and V transpose. All of them are matrices. U is of size M cross M. Our sigma is of size M cross N, and our Vt is of size after transpose as N cross N. Since it's a square matrix, size is not going to change, and if we multiply these together, we are going to end up with M cross N matrices. Now, if you compare it with the form that we write for M cross N, it looks very similar. So there we write PD P transpose, and this was the case of eigen decomposition, but which was applicable only to the square matrix. So we can say that SVD is a generic form of eigen decomposition that generalizes beyond the square matrix. Now, how we should get a better visualization of singular value decomposition? Let us try to think in terms of transformations. When we were talking about the initial concepts of linear algebra, specifically in the topic of analytical geometry and linear transformations, we mentioned that if we are given any matrix A and we multiply it by X, then we can always say that a linear transformation obtained through A, it would either result in stretching, or it would result in rotation, or it would result in some shearing. Basically, shearing is also a special case of rotation and stretching combined. So we can say that rotation and stretching are the two important tasks that are fulfilled by transformation, which is multiplication by A. Now, let us say that we are given some square matrix, which looks like 3, 3, 4, 4, 9, 1, 0. I am writing this particular matrix arbitrarily. And now if we multiply this matrix with any other vector, we can also change the dimensions of a vector. So for example, we have a 3 cross 1 vector and we multiply it by 10 cross 3a. that means the size of A in some arbit case is 10 cross 3 and it is multiplied by 3 cross 1 vector, you would clearly see that the resultant vector would be of size 10 cross 1. So basically we can shift a vector all the way from 3 to R10. Similarly, we can intelligently define this transformation matrix in a way that we can go from R10 to R3. That is, if we multiply it with some other matrix size, if we have an R10 vector, we can come back to R3. So these transformations, although would look complex, that okay, there was some vector represented with respect to a non-standard basis, and after certain transformations, it was rotated as well as it was stretched. And we know that this can be done by multiplying it by a matrix. But what SVD does, it tells us that these complex, although linear transformations can be expressed into simpler components where we are doing some rotations, let us say V transpose, and that will give us some vectors along the standard basis. And then we are doing the stretching. And whenever we talk about stretching with respect to standard basis, we are essentially talking about multiplication with the diagonal matrix. And in this case, that stretching is achieved by multiplying this vector by a diagonal, all the diagonal elements contained in the in sigma. And finally, we have to give it back to the U. That means now that all the space has been changed, and now we have to rotate it back. So the sequence of these three steps when put together gives us U sigma V transpose, and it applies to the matrix of any size. Now the question arises how we can identify what should be the value of U, what should be the value of V, and what should be the value of sigma. And to do that, we will use our another beautiful theorem that we learned in the last lecture, what we call as spectral theorem. Just a quick refresher, spectral theorem says that if S is symmetric, we can always identify a matrix P which will contain the basis that will sweep Rn if this is size n cross n, and this basis will comprise of eigen values. Of course, I am stating it in more like a layman rather than a typical mathematician, so that you can relate to it how that would apply to the case of a non-square matrix. Now, if we are given a matrix A, if we take its transpose and multiply by A, does not matter what is the dimension of A. Let us say this is m cross n, and then transpose. If the dimension of A is m cross n, its transpose is going to be n cross m, and A would again be m cross n. And if we take the inner product, we are going to get a resultant matrix of size n cross n, which is going to be square as well as symmetric. Similarly, when we talk about A transpose, we are going to end up with m cross m matrix if we again go with the same dimensions, which again would be symmetric as well as square matrix, and as a result of which we would be able to apply the spectral theorem to obtain the basis. So what we will do, we will take the A transpose A, and we know that for A transpose A, we can always write this in the form PD, P transpose. Let us say that that the SVD would apply to our matrix A. That would mean it would also apply to A transpose as well as A, and we can simply substitute the decomposed form because our question is what would be the values of sigma, U, and V. So we will write P here, and A can also be written as and then its transpose, then A can be written as V transpose. When you solve it, it becomes V transpose transpose sigma transpose U transpose, and this becomes U and sigma and V transpose. Also, when we talk about specifics of SVD, SVD theorem also states that whenever we are talking about U and V are going to be orthogonal matrix, and guaranteeing that these are orthogonal matrix, that would mean that the V transpose V equal to identity matrix as well as U transpose U equal to identity matrix, because UT equal to U inverse if we are talking about orthogonal matrix. So that would mean A transpose A can be written as V sigma transpose sigma V transpose. And since this, as we said, this is going to be a diagonal matrix, the transpose at its square can be written as sigma 1 square, sigma 2 square, sigma 3 square, and so on. And here we are going to have Vt. Now, if we look at this thing carefully, what we are going to observe, we will see that if we compare this with the form, this is actually just V, P D P transpose, we can easily write this as P is equivalent to V, D is equivalent to our sigma 1, sigma 2, sigma 3, and so on square, and P is equivalent to Vt. And we know that since this is a square symmetric matrix, our P in this case is going to be the collection of eigenvectors obtained for ATA, and when we put these all together, take the inverse, that is going to be PT. So by knowing A, pre-multiplying by it by transpose, calculating eigenvalues, eigenvectors, performing eigen decomposition gives us the value of V that we will use to determine V transpose in our SVD form. Similarly, as we did ATA, we can also calculate A transpose. And when we do A transpose, it looks like U sigma V transpose, U sigma V transpose and its transpose again, which can be written as U sigma V transpose, V sigma transpose U transpose, which equal to U sigma sigma transpose U transpose, which again can be written as U1 sigma 1 square sigma 2 square all the way till sigma m square, and this would be UT. Again, what we will do, we will take product of A and A transpose and compare it with PD P transpose, as this is also going to be square and symmetric. Now, one may argue that what would be the similarities and dissimilarities in A transpose and A transpose A. Of course, the dimensions are going to be different. This is if A is of dimensions m cross n, A transpose is going to be of size m cross m, and A transpose A is going to be of size n cross n. Also, their eigenvalues are going to be same. So eigenvalues in case 1 would be same as eigenvalues as in case 2. Now, since their dimensions are inherently different, their eigenvectors need not be equal, not necessarily be equal. So eigenvectors would not be equal for these two cases. In some cases that may be a coincidence, but in general these eigenvectors are not going to be equal, and that's what would be the distinction between U and V. Also, when we talk about eigenvalues are going to be same, we are typically talking about non-zero eigenvalues for A transpose A and A transpose, they are going to be same. So now just by looking at A transpose A, we can determine what is the value of U, what is the value of V, and we can put the lambdas, and you know that diagonal, so lambda 1 sigma 1 square would be equal to lambda 1, sigma 2 square would be equal to lambda 2, and so on. And for everything that is non-zero, so if we have size m cross n, that would, and if m is greater than n, let us say, then the size of sigma is going to be m cross n. I'm talking about this big sigma here, and along the diagonals we will have these sigma square, sigma 2 square, which are the individual elements of this sigma matrix. And since m is greater than n, all the values after n plus 1 to m, they are going to be 0. And hence we call that as the padding. And sometimes you will see that to avoid this padding, SVDs is described in terms of the ranks. That means rather than writing the first matrix as a square matrix, we already start with m cross k and then write sigma as k cross k followed by another k cross k element, so that the size k cross n matrix, so that the padding is not required. But I prefer this general form because this is without the loss of generality. Now, one simple interpretation of SVD is that now we have factorized our matrix, which was so complex. M cross n matrix is now factorized into two simple square matrix represented by dimensions m cross m, n cross n, and these u and v transpose, they represent some rotations happening. And we have reduced scaling that is happening along the diagonals as sigma 1 square, sigma 2 square, sigma 3 square, which are in turn are closely related to the eigenvalues of AA1, AA2, and so on. So this factorization would help us develop an intuition of K rank approximation. How it would help us develop K rank approximation? Because we will arrange eigenvalues in the descending orders, or sigma 1 square, sigma 2 square, sigma 3 square, they would be arranged in the descending order here. And we call this diagonal elements as the singular values. It has nothing to do with the singularity that we learn in terms of calculation of determinants and such, but here singular would refer to the diagonal elements of our diagonal matrix, and that would be multiplied by our two rotation vectors, which is u and v transpose. And talking about the geometric interpretation in 2 dimensions, this is exactly same what we learned in the case of eigen decomposition. We are doing some rotation followed by stretching and then sending it back. However, the fundamental difference between SVD and eigen decomposition, other than being a matrix, being a square or non-square, is that SVD also allows the change of dimensions, as we just saw the example of R10 to R square and R square to R10 and so on. Now, from machine learning perspective, we will use these sigma 1 square, sigma 2 square to identify the low dimension representation, which would be the topic of next video. And we will also look at one example. I have posted some codes in the comment section that how you can actually verify the eigenvalues constitute V and eigenvectors of A transpose A constitute V and A transpose constitute U. And you can run that example on your Python notebooks and get full view that what this SVD is really doing. In next lecture, we will solve some examples and also talk about the K rank approximation. Thank you.